Have you ever stopped to wonder how your phone can translate a sign in another language instantly? Or how facial recognition just works? Well, behind a lot of that magic is a technology called a neural network. Today, we're going to pull back the curtain and demystify how these amazing systems actually learn to think. All right, to get our heads around this, we're going to start with a really simple challenge. We're going to look at a task that you and I find completely effortless, but is, believe it or not, a total nightmare to try and teach a computer using traditional code. Just look at these two images. On the left, a nice, clean number 3. On the right, a kinda sloppy, low-resolution 3. Now, your brain, my brain, we instantly know they're both the number 3, right? It doesn't even have to think about it. It sees the core idea of threeness in both, despite the pixels being totally different. Okay, now imagine you had to explain to a computer line by line exactly what makes a 3. You could say, well, it's two little arcs on top of each other. But what about all the different angles, sizes, and handwriting styles? The problem suddenly becomes impossibly complex. So we need a totally different way of thinking about this, an approach that's actually inspired by our own brains. To understand this new approach, we're going to use a simple and hopefully fun analogy. Picture this. We're starting a detective agency, and its one and only job is to look at photos and figure out if there's a koala in them. We'll call it the Koala Detective Agency. So, on the ground floor of our agency, we have the specialists. Each of these student detectives has a very, very specific job. One student only looks for koala eyes. That's it. Another is an expert on koala noses. A third, they're the koala ear expert. See, they're breaking this huge problem of find the koala into tiny, bite-sized pieces. Now, one level up, we have the manager. This student doesn't even look at the photo. Nope. Instead, they just get reports from the specialists down below. The eye specialist says, I'm 80% sure I see eyes. The nose specialist says, 95% confident on the nose. The manager takes all these reports and combines them to spot a bigger pattern, like a koala face. And at the very top of the food chain, we've got the CEO. This student gets the face report from one manager, maybe a fuzzy body report from another manager, and so on. They weigh all this high-level info and make the final executive decision, yes, it's a koala, or no, that's just a fuzzy cat. So you see the flow, right? It's this beautiful, layered process. Information starts with simple little features at the bottom: eyes, nose, ears. That information flows up and gets combined into more complex ideas in the middle, like a face. And it all leads to one final sophisticated decision at the very top. It's teamwork. Okay, that was the fun part. Now for the really cool part. Let's take our little detective agency and see how it maps, almost perfectly, onto the real technology of a neural network. And this is the aha moment. Every single student detective in our agency, in the real tech, that's called a neuron. The different teams, the specialists, the managers, the CEO, those are the different layers of the network. And how much importance a manager gives to a clue from a specialist, that's what we call a weight. So what is a neuron, really? It's actually way simpler than it sounds. For our purposes, a neuron is just a little container that holds a number between 0 and 1. We call this its activation. Think of it as that confidence score. An activation of 0.9 is like a detective screaming, I am 90% sure I found that koala nose. It's firing. So how does a neuron decide what its activation number should be? Well, it does a little bit of math. It looks at all the activations from the neurons in the layer below it. Each of those incoming signals is multiplied by a weight, which, remember, is just its importance. So a really important clue, like a big koala nose, gets a high weight. All these weighted scores get added together, and that gives the neuron its result. Then there's one last little tweak. A number called a bias is added. You can think of this as a neuron's personality. Is it naturally optimistic and quick to say yes? It'll have a positive bias. Is it skeptical and needs a ton of evidence? It'll have a negative bias. That final total is then squished down into our 0 to 1 activation score. And that's it. That's the basic calculation every single neuron does. So we've got this structure, layers and layers of these little calculators. But here's the billion-dollar question. How does it learn? How does it figure out what the perfect setting should be for all those thousands of weights and biases to actually solve a problem? Let's jump back to our Koala Detective Agency. On their first day, they have no idea what they're doing. All their weights are just random. So they look at a picture, make a totally random guess, and then a supervisor who already knows the right answer tells them, nope, you were wrong. That actually was a koala. That feedback, that is everything. This is the learning loop, what we call training. First, the network makes a guess. That's forward propagation. Then it checks the answer and calculates its error, how wrong it was. And here comes the magic part. That error signal gets sent backward through the whole network. This is called backpropagation. The CEO tells the managers which clues led them astray. The managers tell the specialists, hey, you gave way too much weight to that pointy ear clue. Koalas have round ears. Turn that weight down. Every neuron adjusts its weights and biases just a tiny bit to be better next time. And it does this over and over and over again, millions of times. And to give you a sense of scale, a pretty simple network, one that just learns to recognize handwritten numbers, has about 13,000 of these parameters. 13,000 little dials and knobs that need to be tweaked. Learning is just the process of the computer finding the perfect setting for every single one of those dials all on its own. So we've covered the structure and we've covered how they learn. Now for the so what. Why does this matter? Well, the simple idea of layered neurons learning from their mistakes is the engine behind some of the most mind-blowing technology that we use every single day. It's right there in your pocket, doing real-time language translation. It's what unlocks your phone with your face. This tech is used to forecast everything from stock prices to the weather. Heck, it can even compose original music. And maybe most importantly, it's the core technology that allows self-driving cars to see and identify everything around them. So here's the big takeaway. We didn't give the computer a giant list of rules for what a 3 looks like. We just built a system that has the ability to learn its own rules just by looking at examples. We started with something simple like a number or a koala, but the potential here is practically limitless, which really just leaves one big question. What should we teach them to do next?